1.1 is on polynomial functions. Okay, so we've talked about polynomials before. So polynomials look like a to the n, x to the n plus. Really long thing. I'm not going to read that all out. But basically, the a to the n's are your coefficients. And your coefficients have to be real numbers. You can't have any i's. Okay? The n's, so your exponents, have to be non-negative. So you can't have any, like, you can't have x to the negative 3. But you could have x to the 3. Okay? So that's what's going to make a polynomial. We say it's of one variable if there's only one variable in it. So it says state the degree and leading coefficient of each polynomial in one variable. We've done this before. We know the word degree and we know leading coefficient. So if I have 7z cubed minus 4z squared plus z, yes, it is a polynomial in one variable. The one variable is z. Your degree is your highest exponent. So the highest exponent here is 3. And your leading coefficient is, when you look at that term that had the highest exponent, it's the number in the front. So it's going to be a 7. So the next one, is it a polynomial in one variable? No, because you have a and b, right? So this is no. And so when that happens, we don't have to do the degree or the leading coefficient. We like those ones. All right, the next one, polynomial in one variable. It is not a polynomial. Why is it not in this case? Yeah, Catherine? Exactly. You have c to the negative 1. Those are actually what we call rational functions when you have like divide by whatever. So this is a no. Lexi, are you finishing your? So the next one, 9y minus 8 plus 3y squared plus, that should be y to the 4th. I forgot to raise it. So let's first rewrite. We always write our polynomials in descending order, right? Descending power. So I'm going to start with my highest degree, y to the 4th. I'm going to have plus 3y squared plus 9y minus 8. So I write it so that the exponents are going down. Yes, this is a polynomial in one variable. When I look at my term in the front, now that I've written it in the correct order, my degree is 4, and my leading coefficient is 1. So we're going to talk a little bit about parent functions. So we did this in the last chapter. We did that very fun math aerobics. Do you guys remember math aerobics? How can you forget, right? So we did y equals x squared, and we would flip it over, we would move right, we'd move left, move up and down. Okay, but our basic parent function for a parabola was just plain y equals x squared, right? It wasn't x squared plus 1 or anything like that. So parent functions are the most basic form for that degree. So if I have y equals x, it's y equals x to the first. And that's just a line, right? So the line has a y-intercept of 0, and the slope is 1. It goes up 1, right 1, up 1, right 1. It goes up like that. So sometimes you might see this written as y equals 1x plus 0. So it's in the mx plus b form. But just it's the same as y equals x. That's the most basic line. So if I have y equals x squared, we've talked about that before. You could do a little t-table if you get stuck, but we know what it looks like. It goes through 0, 0. We have 1, 1. We have 2, 4. We have negative 1, 1, negative 2, 4, right? We've graphed this a million times in the last chapter. 1, 1, 2, 4. This one. Okay, so if we have y equals x cubed, do you guys remember what this shape is? You know this. We've mentioned it briefly. We haven't talked much. Yeah? Not quite a parabola.
Like the thing that goes, like the S.
It's kind of like a little squiggly one. I call it the snake function. I don't know why I call it the snake function. To me, it looks like a snake like slithering in the grass. I don't know. So we have a little curve like that. Okay, and you could see some of the points. It goes through 0, 0, 1, 1. But when I plug in 2, right, 2 cubed is 8. So it shoots up really fast, 2, 8. Okay, so now let's compare y equals x to the 4th to one that we already know. Okay, any ideas on what x to the 4th will look like? It's going to also look like a parabola, right? So Ariana did a little parabola shape. Okay, but it's a little bit different. Okay, so let's think about the t-table for this one. If I plug in 0, I do get 0. If I plug in 1, I still get 1. Right? But if I plug in 2, when I do 2 to the 4th, it goes up really, really fast. It goes up to 16. So if I'm graphing this, I have 2, and then we'll say this is 16. Oh, perfect. Okay. So I get 2, 16, 1, 1. I'm kind of exaggerating the x-axis a little bit. 0, 0, and so on. So it shoots up much, much faster than the y equals x squared. If I draw them on top of each other, this is where the 16 is for the other one. Right, so it goes through the same point at 1, 1, but then it shoots up really fast. Do you guys see what I'm saying? But there's also something else that's different. So not only are the ends like stretched out, kind of like a vertical stretch almost, but in between -1 and 1, there's something weird happening to this graph. Okay, and it's not like how I just drew it on that on top of the parabola. Okay, so between -1 and 1. So let's think about it. Let's go back to the y equals x squared. If I plug in 1/2 and I square it, what do I get? 1/4, right? 1/2 times 1/2 is 1/4. If I plug in 1/2 and I raise it to the 4th, what do I get? 1/16. Which one's bigger? 1/4. It's higher, right? So what ends up happening is along the bottom, like between 0 and 1, it's really, really flat. Those values are so close to 0. They're tiny. Like 1/16 is very tiny. How do you graph that? Really close to the axis. And then once you get to 1, that's when it shoots up super fast. Okay, so it's almost like flattened out on the bottom. So it's flattened out until you get to a height of 1, and then it shoots up super fast. It almost looks vertical. It's not vertical, but it almost is. Do you guys understand what I'm saying? So anything where you have start to have those larger degrees, when you're close to 0, so between -1 and 1, you're really close to the axis. But when you're bigger than 1, it's going to become an even bigger number. So that's the same thing that's happening to x to the 5th. Between -1 and 1, it's super flat. But then once we get to a height of 1, it shoots up super, super fast. So it's just kind of flat. It's obviously not flat, right? But it looks almost flat. Okay. So we're going to talk a little bit about transformations. I know it makes you sweat a little bit. Oh my God, transformations. I saw all of you guys whip your head over like, what? Okay, we're only going to talk about it for these two examples. And then we're going to learn how to graph without transformations. So it says sketch the graph of f of x equals -x cubed plus 2. So the first thing to notice is the shape of the graph. It's an x cubed shape, right? Okay, but we have a negative. So when we have a negative x cubed, there's a reflection over the x-axis. Okay, but then what about the plus 2? What does that do? Exactly, up 2. Do you guys remember all these? We talked about them last semester. So if I'm doing a rough sketch, instead of starting at 0, 0, I've now shifted up 2, and instead of going up for the little snake function, I'm going down. It's flipped over. So it looks just like that. That's a little rough sketch of what we have. So the next one, if I have f of x equals -x squared minus 4, the shape is a parabola, x squared. The negative means that you reflect over the x-axis. So instead of going upwards, it now goes downwards, the downwards parabola. And then the minus 4 means that we go down 4. So if we put it all together, 1, 2, 3, 4, we have a parabola that starts at 0, -4, and it's a downwards parabola. Yes?
Sorry, the number 1, was it that shape because it was being 3?
Yep, because it said x cubed, yep. So we could have different things. In chapter 5, we only dealt with parabolas, but now we could have different shapes. Okay, the things that we're going to talk about today are the ends of a graph. There could be lots of things happening in the middle of a graph. I could have crazy graphs that look like this. Like we could learn how to graph things that look like that, right? But what I'm going to worry about today is only the ends of the graph. Okay, so I'm going to talk about end behavior. So that's what this next thing is about. So end behavior. So it says the trend in the y values of a function as the x values approach positive and negative infinity. Kind of scary looking. It's just saying what's happening on the ends. Are they both going up, like holding my hands up in the air? Are they both going down? Or are they doing what Mr. Morrison calls the John Travolta? Do you guys know what I'm saying? Like that? Like this and this. You guys have no idea who John Travolta is. I see it with blank stares. Who are you talking about? All right, so that's what we're talking about. The ends of the graph. What is happening to the ends of the graph? So the first one, the polynomial has odd degree, and the leading coefficient is positive. So I want you to think of 3 different things. These are our 3. I can count 4. We can think of 4 different things. Okay, so which one is this? leading coefficient is positive and it has an odd degree. Which of the four am I going to think of? I'm going to think of positive x cubed. Okay, so this one's going to look like y equals positive x cubed. So that's kind of our most basic thing that is odd. It has a positive leading coefficient. We don't do y equals x. We think of x cubed instead. Okay, so if I'm talking about the ends only, right, x cubed goes like that. So the ends of it are going to be up and down. So here's what we're dealing with, the ends. So if anything is odd degree and has a leading coefficient that's positive, the ends are always going to look like that. And like I said, it doesn't matter what's happening in the middle. You can have lots of bumps in the middle, but we at least know what the ends are doing. Okay, it's going to help us to graph it. So that's why I kind of leave it as dotted in between, because I don't know what's happening in the middle. Okay, so what if the leading coefficient is negative and it's odd degree? Well, if it's odd degree, it's going to be like x cubed, right? And if it's negative, you're going to do, it flips it over, negative x cubed. So we're going to have looks like y equals negative x cubed. So that's where it goes downwards, right? So you can do a dotted line first if you want, or you can just draw the ends darker, it doesn't matter. Okay, so that's what we're talking about for this one. The ends are going to look like that. Okay, if it has even degree, the leading coefficient is positive. So even degree and a positive leading coefficient, it's going to look like which one? Positive x squared, right? And positive x squared is where your two ends are going up because it was like the parabola. And if you have an even degree but the leading coefficient is negative, this is going to look like y equals negative x squared. So that's where both of the ends are going down. So there's four possibilities. They're either both up, both down, down to up, or up to down. Okay, now we write this in a weird way. So this is the only thing that people don't like about end behavior is how I have you write it. And I'm very nice on your homework. I do like little blanks. You just fill in the blanks. Okay, so here's what we write when we talk about end behavior. So think about a point that's over here. A point that is on that side, in the first quadrant, right? Is the x value positive or negative? Positive. Is the y value positive or negative? Positive. Okay. What about down here? Negative, negative. Okay, that's what we're going to worry about. We're going to worry about the signs. So what I write is I say as x goes to positive infinity. So as x goes to infinity, y goes to infinity. So it's a weird notation. What we're saying is the x values get larger and larger and larger. So as I go to 55 billion, right, y is also getting larger and larger and larger. Do you guys see? It's like a point way out there in the distance is up, up. Okay, now this one. I say as x goes to negative infinity, where do the y values go? Do they go up or down? Are they positive or negative? Right, y goes to negative infinity. So it's any point that's over there in the third quadrant is negative, negative, right? X values are negative, y values are negative. So about number 2, so below it, we're going to say as x goes to positive infinity. So as I go off to the right and I get bigger and bigger and bigger, the y values go down. The y values get smaller and smaller and smaller. So it's going to be y goes to negative infinity. I shouldn't say smaller. They get even more negative. All right, and then on the left side, we're going to say as x goes to negative infinity. So as I go to the left, as x values go negative, y values become positive, right? Y goes to infinity. Do you understand how I'm filling this in? The first few years I taught this, people were just like, what? I guess I got better at explaining it, because now people are like, oh yeah, this is fine. All right, so over here, I'm going to say as x goes to infinity, y goes to infinity. And on the left, I'm going to say as x goes to negative infinity, is y going to positive or negative? Y goes to infinity, right? It's still going up. So they can go to the same, like both of those are going up. Number 2, so I'm going to say as x goes to infinity, y goes to negative infinity. I'm going to say as x goes to negative infinity, y goes to negative infinity. All right, so let's try it out. Let's see if we understand end behavior. And like I said, on your homework, I'll write out as x arrow blank, as y arrow blank. You know, like, or sorry, not as y goes. As x arrow blank, y arrow blank. So that way you just fill in the infinities or negative infinities. Okay, so we'll go a step extra. So we'll do the leading coefficient, we'll do the degree, and then we'll talk about the end behavior. So number 1a, so it says p of x equals negative x to the fourth plus 6x cubed minus x plus 9. Your leading coefficient is negative 1. The degree is 4. Negative 1 is a negative number, and the degree is an even number. So if you have a negative leading coefficient and an even degree, think about what it's going to look like. It's going to be like negative x squared. So we do a little rough sketch of what negative x squared looks like. And then that's where on your homework I'll have those little blanks for you. So we'll write it out on this one. So we'll say as x arrow infinity, so as x goes to infinity, comma, y goes to negative infinity. And on the left side, I'm going to say as x goes to negative infinity, y goes to negative infinity. Make sense? All right, the next one. Your leading coefficient is 2. Your degree is 5. So it is positive and odd. Don't get confused. Don't see the 2 and think, oh, it's even. No, that's just telling you if it's positive or negative. It's telling you if it goes up or down, or if it's, I guess, up or down if it's a parabola. All right, end behavior. So it's positive and odd. So it's going to look like x cubed, exactly. So I do a little rough sketch of x cubed to help me. That little sketch helps a lot. And I write it out. So I say as x arrow infinity, as x goes to infinity, y goes to infinity. And on the left side, I say as x goes to negative infinity, y goes to negative infinity. Another room. Are we good with end behavior? Okay, what if you have a graph already? Just look at the ends, right? It's like this and this. So there's 4 possibilities. Here are the 4 possibilities. You don't have to draw these. Which ends does it look like? It looks like this one. That is negative x cubed, right? Looks like negative x cubed on the ends. So that means that it's odd degree, negative leading coefficient. So odd and negative. All right, how about the next one? On the ends, they both go up. So which ones does it look like? X squared, right? So like y equals x squared. So it's even degree, positive leading coefficient. That's all I want. So why did I spend an entire class period talking about end behavior? Because we use this when we graph. So that's the whole point. We're learning how to graph. So we're going to do that on these next couple examples. So steps for graphing, just like, graphing other things, like parabolas, we always found the x-intercepts. We found the y-intercept. Same idea. We're still going to do that. So we're going to find the x-intercepts. We sometimes call those zeros. We're going to find the y-intercept. We're going to plot all of those. And then we're also going to consider the end behavior. Sometimes things might have what we call multiplicity. So we'll talk a little bit about this. We'll talk more about this in a second. But basically, multiplicity means, like, if you have something that looks like, you can barely read it there, so I'll rewrite it. X minus 4 squared. What that really is x minus 4 times itself, x minus 4. So if I'm finding the x-intercepts, I'm setting the y equal to 0. And 4 is your answer. But 4 isn't just your answer one time. How many times would it be a solution? 2. From here and from here. Yeah, that's okay. So it's an answer twice. Okay, so when something's an answer twice, we say it has multiplicity 2. If it's an answer 3 times, we say it has multiplicity 3. If it's 4 times, multiplicity 4. Does this make sense? If it's just one time, we don't say it has multiplicity. It's kind of weird. There's not a multiple of it, right? Okay, so anyway, so if something's an answer twice, then when you zoom in on that point, it's going to look like a parabola at that 0. It's going to like bounce. It's going to hit the curve, or it's going to hit the 0, and it's going to bounce back up. Or it might go from the other way. So it might hit the curve and then bounce back down. Kind of depends on the end behavior, so we'll talk more about that. Okay, what shape do you think it will be if it was an answer 3 times? What if I crossed out this 2 and I made that a 3? So it's an answer 3 times, has multiplicity 3. What shape do you think it will look like? Like a little stinky one, right? It's going to go through like an x cubed. So at that 4, it's either going to go through like that, or it's going to go through like that. And we determine that with the end behavior. Does this kind of make sense? So multiplicity tells you how many times something's an answer, and then it tells you, when you zoom in on that 0, on the x-intercept, what shape it's going through. Now think about it. If something has multiplicity 1, what shape is it going to go through? Like y equals x, right? Like a line. It's just going to go straight through. Okay, it's only when it's like multiplicity 2 or whatever that it really matters. Okay, so sketch a graph of the following function. So we're going to go through all these steps. We're going to find the x-intercept. We're going to find the y-intercept. Sometimes it says make a table for x values that are between the zeros if needed. Most of the time, you're not going to need to do that. Okay, so let's find the x-intercepts. In order to find an x-intercept, I plug in 0 for what value? For the f of x, for the y, good. So I'm going to have 0 equals x cubed minus x squared minus 4x plus 4. And it's a good thing your homework had this review on there. What do we have to do? Factor by grouping, correct. Split it down the middle. We pull out the x squared. We have an x minus 1. I know I want an x minus 1. Is it possible? Yeah, I have to pull out a negative 4. Because when I multiply that negative 4 in, it would be negative 4x plus 4, like I need. Okay, I have a common factor. I have the x minus 1. So I pull my entire x minus 1 to the front. When I do that, I have x squared minus 4 left. Now I factor. So I do x plus 2, I do x minus 2. I have 3 solutions. Now you guys are all past the point where you need to say 0 equals x minus 1, 0 equals x plus 2. You guys can do that, right? So my 3 solutions are 1, negative 2, and 2. And what those are x-intercepts. So they're really the points 1, comma 0, negative 2, comma 0, and 2, comma 0, because we plugged in 0 for y in order to find those points. So we plot them. Yes, I made a very tiny graph. So mean. You guys have young eyes. You can do this. I struggle. So I have 1, 0, negative 2, 0, and 2, 0. All right, we're done with the x-intercepts. That's the hard part. Y-intercept, do you guys know it right away? You plug in 0 for the x. I heard someone say it. 4, yep. Because when you plug in 0 for x, this is gone, this is gone, this is gone. You just end up with that last number. It's 4. So you have 0, comma 4. Okay, so now it's all about connecting the dots. Now this is not connecting the dots like my 5-year-old connects the dots. Like very, you know how like 5-year-olds will be like, like very straight lines. We are not going to do straight lines. And even though I say this multiple times, we are not going to do straight lines for polynomials. People will still do straight lines. So what we're doing is we're connecting with curvy lines. We always say polynomials are smooth and continuous. So here's the thing, we don't know how to connect them yet. We're missing information. We need the end behavior. This is why we do end behavior. Okay, so looking at the very first term, is it odd or positive? Or odd or even? Jeez, I need a nap. Odd or even? Odd. Is it positive or negative? Positive. See, I told you odd and positive. All right, so it's going to look like positive x cubed. Right? That's what the very first term is, x cubed. That's what it's going to look like on the ends. So we draw those in. We draw in the ends. Because we look at the very first term, x cubed is the end behavior. Okay, now we connect the points, but we don't, like those dots aren't necessarily like turning points, right? Remember if it has multiplicity 1, air quotes, we don't ever say multiplicity 1. There wasn't multiplicity basically. We go straight through. So we're going straight through this 0. We go up to this point. We go straight through the next 0. We have to curve somewhere to go back up. And then we're there. You see how we're connecting? You're never going to cross anywhere but those 3 points. So I always get students that draw this. Let me draw it again. That like make it come back down, right? They always do like weird things like that, but it doesn't make any sense because you're crossing right here, and there wasn't a 0 there. Okay, so you're only crossing at those zeros that you've drawn in.
How do you know how far down to make?
You don't. You don't know exactly how far down this one goes. And that's why I always say, like, draw a rough sketch a lot of times. You could, I mean, with calculus, that's how you really learn. You learn how to find maximums and minimums. And we don't really know if this is really the maximum either. It could have gone past here. And that's where some people are very, very precise and want to draw a little t-table and find extra points. If you want to find extra points, you can. What I'm worried about are these 3 points where it's crossing and the end behavior. I want to make sure that you have all of those things. So it's kind of a rough sketch. We don't know how high or low it's going though. All right, let's do the next one. So f of x equals x to the 4th minus 5x squared plus 4. So if I'm finding my x-intercepts, I'm going to plug in 0 for y. Okay. This isn't one where we can split the middle. There's not 4 terms. How do we do this? We factor it with the 2 sets of parentheses, and what do we put at the beginning? X squared, right? So we've done these before, but it's been a long time. So x squared and x squared. So to make that positive 4 and the outer and inner to combine to be negative 5, I'm going to need a negative 4 and a negative 1. Now you see that it goes again. X plus 2, x minus 2, x plus 1, x minus 1. So my x-intercepts are negative 2, 2, negative 1, and 1. So they're very, very close to each other. A lot of people think also when they have 4 points like that, they're like, oh, it's just a straight line on the x-axis, and they just connect a straight line. That doesn't work. Those are the only places where it's equal to 0 for the y, right? Like, you can't just like draw a straight line. That's why we say the polynomials are smooth and curvy. Okay, y-intercept, what's it? 4. Okay, end behavior. The very first term is x to the 4th. It's even, and it's positive. So it's going to look like x squared on the ends. So all I do is I draw the ends of the graph. Can you tell what shape this is? It's a letter. It's a W. Goes down and through. Right, so it's looking like that. Yes?
How do you know to do that plus 2 plus 1?
Because we set each one equal to 0. It's like saying x plus 2 equals 0, x minus 2 equals 0, x plus 1 equals 0, and x minus 1 equals 0. Because we're setting equal to 0 and it's factor, so we set each piece equal to 0. It's like when you factor an equation, like let's say you have 3x minus 2, 4x plus 5 equals 0. We usually write a step in between where we set it equal to 0, like each piece equal to 0, and we solve them. That's what we're doing. We just kind of, like, when they're really easy to see what they are, like this is negative 2, this will be 2. We just kind of okay. All right. And the very last one, I'm going to have you guys change this because we don't actually learn how to factor that until later on in the chapter. So I'm going to give you another one. So we're going to do x minus 1 squared times x plus 3. So we're going to do one that involves multiplicity. So x minus 1 squared times x plus 3. All right, so if I want to find the x-intercepts, luckily this one's already factored for us, right? So I plug in 0 for the y, and I set each piece equal to 0, so it's like x minus 1 is equal to 0, X minus 1 is equal to 0. X plus 3 is equal to 0. Do you guys see how this is going to be the same solution? So you get x equals 1 twice. So it has multiplicity 2. There was a movie from like the 90s called Multiplicity. I think about it that every single time. It was terrible. I haven't even seen it. It was awful. It's about cloning. Sorry for any people watching my YouTube video that might have been associated with that movie. All right, x plus 3. So I get x equals negative 3. So I have at 1 and I have at negative 3. My y-intercept is a little bit harder now, but still not too bad. I plug in 0 for x, so I have 0 minus 1 squared and 0 plus 3. So I get negative 1 squared times 3. So negative 1 times itself is 1. So I end up getting 3. So I have the point 0, comma 3 for my my y-intercept. Like that. Now I have my end behavior. My end behavior. If I multiply this all out, this is kind of the tricky part. Do you guys see it? If I have x minus 1 times itself, if I FOILed it out, I would get x squared minus 2x plus 1. It doesn't matter about FOILing it out. Just think about the very first term, x squared. Now if I multiply by an x plus 3, what happens when you multiply by an x plus 3? What's the very first term? X cubed. Do you guys see how this is going to start out with an x cubed? That's all we're worried about for the end behavior, just the very first term. So it's x cubed. So that means that it's going to look like this on the ends. So I'm going to have 1 down and 1 up. Okay, so don't draw this, but I'm going to draw in a different color to show you kind of your thought process as you're doing graphing. So you're like, okay, I'm going to go straight through this one, I'm going to hit this point, and I'm going to go straight through, and then it's like, oh, crap. Do you see what happened? Your end behavior is not matching up. This is why end behavior is so important. I need that multiplicity. If I don't have the multiplicity, my ends do not go in the correct place. Okay, do you guys remember what multiplicity means? So we said that 1 has multiplicity 2. So when I hit 1, it's like it bounces. It makes an x squared shape because it was multiplicity 2. If it was multiplicity 3, it would make that snake shape. But luckily, it's multiplicity 2 because it needs to bounce back up to give me that end behavior. Do you guys see? So when you zoom in, it looks like x squared because it has multiplicity 2. Okay, that's why we need multiplicity. Otherwise, as you're graphing it, you're going to be like, oh, I did something wrong. That's when you always go back and you look. Okay?